Well, good evening. This lecture is about deployable structures and it's about a new technology I have developed. But first of all, I would like to introduce the background of this research. So I'm doing a PhD in the University of Cambridge, and my supervisor is Michael Ramage, and he has a research group that is called Natural Materials. So this is about building architecture of good quality and also without damaging the environment, using natural materials and developing the knowledge of what can be done with timber and with clay. So just to show you some examples about what he does. This is a project that I did in South Africa, and it's done with clay tiles. And it's not only a healthy environment for humans to live, and it has space and ventilation, but it's actually an inspiring space, and also it's sustainable. It's sustainable in many different ways. It's sustainable because it's made with earth tiles, and also because they actually trained the local people to make this architecture. So this is an image of the construction of these clay tiles. So if any of you is interested in building with natural materials, please do have a look at the web page of the Natural Materials Research Group in the University of Cambridge and Michael Ramage's work. And this was done by Light Earth Designs as well, and that is a partnership in between Peter Rich, Timothy Hall, Michael Ramage, and Anna Gatto. So this lecture is about deployable structures, and transforming architecture can be made by the design and the manipulation of deployable structures, which can transform, expand, and contract, and still keep all their structural integrity. Therefore, they allow the maximum transformation with a minimum effort, and they have many different applications. We find applications in architecture, in aerospace, in robotics, and it's also kinetic art. And there are still many more applications in medicine and even astrophysics, actually. Astrophysics are now using origami to explain how the cosmos is evolving. So there are some really fascinating things. Specifically, this lecture is about a new technology I have developed. And in order to explain this, I have to introduce two different types of deployable structures. And these are origami and scissor-hinged. So origami, we all are familiar with origami, and you can use origami as art to make a particular sculpture. But origami, many origami patterns can also fold and unfold. And this inspires many applications for us architects and also engineers and just designers and people from many different backgrounds. So that's why we are very interested in origami, and not just the final product, but the very process of transformation. So this is the work of Ron Resch, who was a geometrist, artist, and computer scientist. And he developed many origami tessellations. And I show these images because it's quite interesting. So we make an interesting origami pattern, and there's always the desire to make that origami pattern into a larger scale. But for any of you, if you've tried, then this is a challenge to actually do something at a larger scale, and we will talk about this later on. I also wanted to show some examples of contemporary research that is currently being done with origami. So this is research done by Kaori Koribayashi Shigetomi, Hiroaki Onoe, Shoji Takeuchi, and basically this is the smallest origami I know of. This is cell origami. So this is at that scale. The scale of this origami is about 50 microns, which is about 0.05 millimeters, so about a hundredth of a millimeter. And the idea is that you have these microplates, these blue microplates here. And these green things that are on top of the microplates, these are cells. So the cell is unifying the microplates. And when these microplates are probed, then they can fold. And the idea is that this research can be used for medical applications. So I'll just show you a video about this. So this is the theoretical model. And this is the live culture. And these cells can be used to grow all sort of microscopic medical devices. But this is some of the current research. This is just to show some of the great variety. And Kuribayashi has a background in engineering. She was also very interested in aerospace applications. And now she's integrating these with her medical knowledge as well, and doing some interesting developments in the field. So this is another example of contemporary research done with origami. And this is particularly a protective ring, and it's actually called rotorigami, and it's done by Poya Sareh, who I think may be in the audience, Pisak Chema Proyong, Mark Emanuelis, Haris Nadine, and Miko Kovac. And as you can see, so this is a drone. This is for indoor applications. So these are the propellers of the drone. It's got 4 propellers. And these are some of the options of how one can protect the propellers. So these are individual protections, and these are universal protections. And this one is fixed, and this one is as well fixed. And the other one is rotary. So if you imagine this ring protecting the propellers, if the ring was fixed and it has an impact, it actually is fighting against the impact. But if the ring can independently rotate from the propellers, then it can absorb some of the moment, some of that force of the impact. So the idea is that the rotary option, the rotary universal option, was more preferable. And then there's also this rotary origami bumper, that this is a deviation from the Miura-Ori pattern, and it's also, well, the Miura-Ori pattern is highly used for engineering applications and aerospace because it has many interesting structural properties, and it's relatively simple to fold. But I think Sareh would be able to tell us more about this. But basically, it has been designed so the Miura-Ori can accommodate that form and can further protect the propellers and the drum. So I'll just show you a film here of this work. I will find the one at 60 degrees. Okay. Okay. So this is a video done, and this is an impact at 60 degrees. And this is fixed. So you can see the ring that is around the propeller is fixed. So there's quite a motion, and there's quite a deformation due to the impact. And yeah, and this one is fixed as well. So the ring is fixed, but it has the origami bumper. And this ring can rotate, so you can see that it's rotating. And therefore, instead of fighting against that impact, it's absorbing part of the impact. So that's why the rotary universal protector is more preferable rather than the fixed one. And this one is both with a rotary ring and also with the origami bumper. So this is another example of contemporary research done with origami, and these are some zipper tubes done by Evgeny Filipov, Tashi, and Paulino. And it's basically, again, using the Miura-Ori pattern and making some tubes. But normally, origami tubes, they can deform in various angles. So they are flexible, and they can expand and contract, but they have too much flexibility on one side or another. And this is interesting on the one hand side, but actually, if you want to create something that is controlled, that can expand and contract, and it can go there, but it can also go there, and it can also go there simultaneously, it lacks structural stability. So what's very interesting about this development in origami is that by actually incorporating and merging 2 of these zipper tubes, the origami gains the structural properties that it didn't have before. So I'm just going to show you another film of this work. So these are the 2 separate tubes that are placed, interlocked with each other in a zipper fashion. And they can also be foldable from different axes. And they can be actuated from one point, from one end. So this is some of the work by Tomohiro Tashi. And this is, for instance, an example of how to make a vault out of origami, thin origami, by means of creating a virtual thickness. So as you can see in the folded state, it's just flat, two-dimensional. But then when it unfolds, it acquires a curvature. So of course, this has been designed with very specific parameters along the curve, and the curve folding along the curve, and all of this works with certain parameters. It cannot happen at any angle. There are specific angles and geometries for which it works, and these are some of the options, design options, and this is a prototype, a build prototype. So now, talking about that issue of building origami at a larger scale is the field of thick origami. So we were saying, when we take an origami pattern, for instance, like this one, so this is the diamond pattern. And when we take any of these patterns and we see that they create structural forms that they can transform, it's very interesting. But when we think about using these origami patterns in an architectural scale, then we want a material that is rigid. So paper is fantastic because at this scale, it can be rigid in the face and it can crease here and it can allow that folding and unfolding. One material is doing all of these things. But at a larger scale, this is quite so far not possible yet. Also, there are some advances in this, actually. But at a larger scale, we need a rigid panel. And rigidity normally comes with thickness. And then if you have, let's say, a zigzag fold with thick panels, then you join the edges of the thick panels, and it's very easy. But if you have a complex origami pattern done with thick panels, you'll find that if you align two creases, then the other ones are incompatible, because instead of having one line in the crease, suddenly you have a thickness coming from all the different edges that are adjoining. So because it is challenging building origami at larger scales, there is the research field of thick origami. And there have been many advances, and in fact, most of the applications so far have been aerospace. There are many satellites and applications online. So I will show you now a development that was done with origami of thick panels. And I chose this one because I found that quite interesting. And this is done by Chen, Pen, and Yu, and they published it in Science in 2015. It's origami of thick panels. So what's interesting is that I've shown you here, this is the diamond pattern, done just zero thickness paper. And this is the diamond pattern. But this one is done with thick panels. So this is a small scale, but this is just a proof of concept. The point is that the thicknesses have been sorted here. So this panel is that small, but you could make it at a larger scale, right? So this was a development that was done published in 2015, and it is still yet to be applied in architecture. And what's interesting as well about what they did with the work is that this is just not a single origami pattern, is that they developed basically our understanding that origami cannot only actually be devised through origami kinetics, but actually through mechanics. So this method can be extended and generalized to other origami patterns, like the waterborne pattern, for instance. So now I have talked about origami so far, and now I would like to talk about a different type of deployable structure, and that is scissor-hinged. So the concept of scissor-hinged is to take 2 bars, for instance. You can do it 2 bars, 3 or 4, but let's specifically talk about 2 bars. And then by putting a pivot, you allow that motion to occur. And then by duplicating the scissors, then you can create potentially large structures, surface, spectacles, art that can expand and they can contract in a controlled manner. So I think this is probably the most well-known example of a scissor-hinged deployable structure, Charles Hoberman. And he's got experiences in expo and toys and kinetic art and components for architecture. But actually, the first person who devised scissor hinge deployable structures at an architectural scale was a Spanish architect, Emilio Pérez Piñero. And this is a prototype that he did, it's a small maquette that was awarded many prizes, a specific prize actually with Felix Candela and quite a few other people. And I talked about this in the lecture I gave here 2 or 3 years ago. So he was the first person that actually did scissor hinge deployable structures at a large scale. So this is a prototype. And as it happens with many projects, is that at time to make it, to finance these projects, then they end up being transportable projects rather than deployable. But so the previous one was a transportable project. So these 2 images. I just have one image for each. So this is done with 3 bars, and this you can see a large prototype that he built in his basically near his city in Spain, and this is an exhibition in Madrid made with 4 bars. So this was in the 60s, and we are lucky enough to have these pictures. But these structures that you can see that are extraordinarily large, these could expand and contract. So he'd get the fabricators and a few people in their vans and cars and go to the countryside and test these prototypes. And then he also got to actually build some projects. And he actually, if you look him up, he's got many interesting collaborations. He collaborated with Salvador Dalí, and he did, he's got a really interesting set of work. So this is a more contemporary project. So these are rare still. So this is the stage we are. It's a relatively new field. And this is an application for a cover of a swimming pool in Seville. And this is done by Felix Escric, another Spanish architect, Juan Pérez Valcárcel, and José Sánchez. And the idea was that in the winter, one could cover the swimming pools, and in the summer, one could take away those covers. So this was a prototype, and here we see the production of the structure of site, how it was brought on site and deployed by a crane through gravity. Well, so this is now where my research work starts, and I specifically started with scissor hinge deployable structures. And at the beginning of my research, I just wanted to understand more. So when you look at this, it looks like a fairly complex thing. But I wanted to understand how these structures work, and I developed, I'm in the process of developing a theory for explanation and innovation. So by actually analyzing and observing the build case studies done with scissor hinged, I derive a set of theory that can also be used for innovation. So basically, what I'm part of my research explaining is that the geometry of the deployable structure can be explained with the geometry achieved by the deployment and the geometry of its morphology. And in order to do this work, I'm using the field of advanced descriptive geometry. Now, the first few slides may seem a bit theoretical, but then later on you will see applications for it. But this is to try and understand what do I mean by the geometry achieved by the deployment, and what do I mean by the geometry of its morphology. So both of these projects, so one is an air cell structures, loose geometry by Angus Brown, and the other one is the cover I have just shown you in Seville by Escric, Valcárcel, and Sánchez. So they are both very different type of projects, both of them. So one is done with scissor hinged, and the other one is done with air cells. But they both have very similar, if not identical, geometry of the morphology and geometry of the deployment. So the geometry achieved by the deployment is a quasi-spherical geometry, and the geometry of the morphology, if you look, is the intersection of 2 lines, and if you repeat this, it makes a grid of squares. So I think you can all see a grid of squares. I think you can all see that both these projects are made by the grid of squares. So here we've got a square, and here we've got a square. There's a diagonal, but that diagonal is exclusively for reinforcement. The geometry is also done by a grid of squares. So through this, I developed a theory of geometry, of infinite geometry, that this is the way I understand it, and there can be infinite combinations of lines, two-dimensional, three-dimensional, of various degrees, degree 1, degree 2, degree 3. There can be different types of solids, regular, no regular, and there can be different types of surfaces. And the possibilities are quite infinite. And when I'm talking about geometry, I'm not talking about triangles or squares. Geometry is everything. Everything that is in space has a geometry. So my hand, my arm, all the veins, all the muscles, is all geometry. So this seems very vast and very abstract. But let's see how this can be used for innovation. So the existing geometries so far for making scissor hinge deployable structures are these. So this is, in essence, the surfaces that have been done so far with scissor hinge deployable structure. And I don't mean this view, I mean the top view, like if you look from above. So if I were to extend this, if I had more of this, I would have here a large surface, and this would be a grid made of triangles. Can you see that it's all made with triangles, right? So far, the surfaces that have been done with scissor hinge, if you looked from the top, there were grids of triangles and squares. So each line that you see would have a scissor from the plan view, and then the elevation view would be something like that. The options of these grids have been so far, they have been done flat, they have been done vaulted or barrel vaulted, and there have been many developments in this field, but that's the way surfaces have been done so far. So what I thought is, well, why couldn't I, for instance, take the intersection of 6 lines? So I want to apply scissors to a new type of surface, to a new type of grid, we could call it. So I take 6 lines, 1, 2, 3, 4, 5, and 6. And now if you follow me, I repeat this 4 times, 1, 2, 3, and 4, and extend the lines, and it gives me that square. Can you see that square here in the center? So this is the square that was derived from intersecting 6 lines, and I'm going to try and apply scissors to this and see what happens. And so far, to make a flat surface and with the scissor units to be perpendicular to the surface. So this square here is this square here. So the first thing I do, let's see if I make this work. Yes. So this is going to be one line. All of these lines are going to have scissors, right? All of these lines are going to have scissors if I look at it from the top of view. So where these lines intersect is absolutely key because I want the nodes to match, don't I? So the first thing is to define these nodes. So there's a node here, there's going to be a node there, there's going to be a node there, there's going to be another node there. And this line that I call segment S1, there are 8 of these segments, and there are 4 of these segments. Now, what I thought is I'm going to take the smallest distance and then see if I can replicate this everywhere else. So this smaller distance in between the intersections of the lines, I'm going to feed there 1 scissor unit. So this is my first. I put a circle just because I have not bothered to measure that distance. I just take it with a compass, let's say, and I call it C1. And then I transfer that distance everywhere else. And for instance, in some places, it's quite ideal because in the segment, in the subsegment B of segment 1, I have 2 of these ones. So that's perfect. So in one place I've got 1 scissor, in one place I've got 2 scissors, but in other places I need smaller scissors, and it all has to match. So ideally I want the smaller scissors in one place to match the smaller scissors in the other place. So I've got one ratio for my scissors that I call C1, and I've got another ratio for other smaller scissors which are essentially the same as the first scissors, but you cut them at one end and then you replicate them. And ideally I can build all of these with only 2 different sizes of scissors, right? And these are some geometrical relationships. these are all geometrical relationships. I have not measured anything with any distance. It's all about the relative ratios. So this is my segment. So this is the first segment S1, where I establish the first scissor unit and I transfer it. And here you see the smaller one. The smaller one is basically like this one, but I cut it here at the end and I mirror it. Now, one of the things is that this is smaller scissor. If you make it too small, then it can limit the mobility. So you don't want to make it too small. So I made it that at least it had to be half or bigger. So then I transferred these in 3 dimensions, and it seemed fairly okay. But here in these intersections, the nodes were not matching. I mean, it could still work, but ideally you want the nodes to match. So I further subdivided it. I divided all the ratios in half. And by doing that, what I was able to do is I was able to separate these two ones, because node 1, this is node 1 of this one, and it's intersecting node 4 of the same one in a different position, and they were incompatible. So I want them to match. I want node 1 to match node 4. And before, one was larger and the other one was smaller. And by halving all of them and separating the different one, now they are completely kinematically compatible. So this is the resulting surface with all of the nodes matching in its expanded state and its contracted state. And of course, this is still the theory. These are still lines in space, and when we build with thickness. But you cannot do everything at once. You first start with the theory, and then you take the next step. So if you were to replicate this, you could create a larger grid, and then it could be called a 6-way grid. And then I thought, well, what if you try and do the same, but with a quasi-spherical surface? So when you transfer this in 3 dimensions, the issue that you have is this, again, the same nodes, node 1 and node 4. It's difficult to see here, but they are not actually clashing. They are not clashing. They are all working fine. But this one and this one, although they are not clashing now, they would clash in the process of contraction. So I thought of 2 different possibilities to solve this problem, and one of them was to reduce the sizes of the scissor units so that they wouldn't clash in the process of deployment. And the other option is to actually change the curvature of the segment so that they match and so that they can actually intersect. So this is where node 1 meets node 4. So before we had these, and one was on top of the other and clashing, and now they are completely, they are exactly in the same place. And you could replicate this in a number of different ways. Now, what was interesting about what I've shown you is that it was not just the design of a new surface that had not been done before, is that this was a method. This is a method that I could apply to any given combination of lines. To any given combination of lines. So if I take a pen and if I take a paper and I do any combination of lines, I could apply the same method to that combination of lines. And of course, some combinations of lines would be more structurally stable. But the beauty of this is that you could also add and remove if things were not structurally stable enough, like if you had a very dense surface here and just fairly empty here. So it's very versatile. So this form generation of method, I called it the form generation method of relative ratios, which so far has been applied to scissors. And the method states that in any given combination of lines, a ratio of various ratios can be found as the relationship of the segments and the subsegments in respect to the number of times that one is contained in the other. So therefore, this has a vast potential, and I built a prototype, but this is still a work in progress. But that prototype was on hold because then I had another idea, which is what I'm going to show soon. So throughout the history of the deployable structures, origami and scissor-hinged have been different types of deployable structures. And I had the idea that if I could apply my form generation method of relative ratios to any given combination of lines, why couldn't I take the segments of a thick origami and make each of these thicknesses with scissors. When I had the idea, I first thought it was outrageous, and I wasn't sure if it was going to work, but it has worked. So the origami is a hinged geometry method. So this is a method in order to unify these two different technologies. And what first one has to do is to take the thick origami and derive the segments from this geometry, and then applied the scissor method. So this is, for instance, the diamond pattern. So here we have it again. So what is that? That hexagon on the top, your top left, is this hexagon. So is this hexagon. So if I take this hexagon, you're looking at it like that way, and I start joining the vertices, I obtain this series of triangles. And then by starting to define the geometry from this point of view, I'm establishing a set of geometrical relationships. Therefore, I do not need to specify which angles they are, because it is inherited within the geometry I am specifying. So there's this. I mean, this looks fairly complex, but essentially, can you see there is a diamond here, and here there's half a diamond. So we are trying to construct half a diamond, and then we just duplicate it. So there's a bigger triangle, and there's a smaller triangle. And the bigger one is obtained by joining these vertices. And here we can see how the smaller one is superposed on the larger one. And here we have the diamond, and how this is replicated in order to make the diamond pattern. And this is how it's done three-dimensionally. And in this case, these two different triangles have been done with equal thicknesses. So the thicknesses are key. So if you can see this, half of this diamond here is this one, right? So, and I have added these segments that are in red, and this is to give the structure more structural stability, because now it's solid, but once I make these scissors, it will be a lattice structure, and it needs more strength. So here it is the same triangle that is here above, but adding the ratios. So it's basically the same process. So here in the center, can you see this is an equilateral triangle? So I choose to divide this in three ratios. So here I have 3 ratios, and they are all the same scissor sizes. And all of these lengths from 0.4 to 6, so segment 4, 6, all of this line is made of the same ratios. So these are exactly the same size of scissor units. So this one is this one. So now, because here I'm going to have one thickness, and then the superposed thickness of the smaller triangle, I have to superpose this. And what I thought is that when I build it with scissors, I actually extend them as if they were a trellis, so that they would be more structurally stable. So for instance, this is these are the other segments of the equilateral triangle, which are also made of 3 C1 ratios. And this one here is the slightly more tricky one here, that is basically for reinforcement by triangulation. And what I do is I put these smaller scissors, and I just cut. Can you see? It's just the same scissor of C1, but I just cut the end off. But I have one rule, and it's the smaller scissor can only be half or bigger than the original scissor, because otherwise, when you build things with thicknesses, it wouldn't allow a good motion of the structure. So when we have this segment, which is equal to this segment, here I show 3 different options for making that segment. So this is one option, and this is another one, and this is another one. And this is just to show clearly. So here I put the same scissor units and at either side, and in the center I put a smaller one. But this smaller one wouldn't allow a good expansion and contraction once you build something with thick bars. I mean, in the theoretical model of lines, it's fine. But once you build things with thickness, it wouldn't, in most ratios, it wouldn't allow a good mobility. So preferably we want larger, smaller scissor units. So this is another option with the smaller scissor units. And here is how it would be duplicated, because we've got here we've got a double thickness, and here we've got a single thickness. So this one would be the double thickness that we have here. But then I did a third option, which is I actually put the first ratio from the center so that I could actually join it. And what this means is that I can join these bars, and these segments can actually be more, these scissors can be actually more structurally stable, because I can unite them not only on the sides, but also in the center. So this is the preferred option. So this is from theory to prototype. So as you can see clearly, before we had these two triangles, the triangle T645 and the blue one. So now these are made by scissors. So here we've got the blue one, and here we've got the bigger one, and these are just for reinforcement. So, and here it is the build prototype, which I have here with me. So I've got this. So the prototype I'm going to show you here, because of issues of building methods, is a prototype of these two. Okay? It's just because I'm going to a larger scale because of my construction methods. I'm going to show you this triangle. So just one single diamond I'm going to show you. And this is the one single diamond of the diamond origami scissor hinge pattern that can expand and contract, and it can also fold. So this is one single diamond, and that one I show you there has 20, and this one has 2. So imagine this done with 20. So this, as you can see, this can expand, and it can also fold and unfold. And these are two completely different types of motion. You could do them together, or they could be completely independent. So when in the origami model, the one face was made of 2 bars, in the origami scissor hinge, it is made of 77 bars and 122 nodes. And this is done with a minimum number of different sizes of bars, which in this case was 6. So this is some images of the prototype I've just shown you. And here, just so that we start thinking as well from scratch, this is the same one, but with 6 faces. So I've just shown you two faces, and this one is 6 faces. So here on your left, you can see the paper model. And this is the origami Osi panels by Chen Peng and Yu. 6 faces of the bigger one I've shown you before. And here we can see this in comparison with the origami scissor hinged pattern. So as you can see, the one with 6 faces can fold and unfold as an origami, but it can also expand and contract. And now I've shown the expansion and contraction at this stage, but it could happen at this stage, or it could happen at this stage. So it has 2 degrees of freedom. And here I'm going to show you a film. So this is the origami folding of the origami scissor hinge pattern next to the diamond. And so the point of this is that this is not a new shape. This is not a new design. It is an advancement. It was not known that could be done. If you ask an expert in the field before this, if you could do a thick origami that expands and contracts, they would say it was impossible. But now it's possible. So this prototype, made of 6 triangulated faces, is made of a total of 744 nodes and 462 bars. But it's only done with 6 different types of bars. And this because I unified, so these 2 layers here, these 2 layers here could have easily been separated. And had it been so, there would have been even less, smaller number of different sizes of bars. But because I wanted to unify it to give it a structural stability, then I ended up with a few more different sizes of bars. But there are still few, only 6. And the next stage was to think, well, is this a single structure, or is this a method that can be extended and generalized? And if so, you have to demonstrate it. So here I took the diamond origami of thick panels, and there are other origami of thick panels, but I chose the origami of thick panels by Champion and Yu because it's a method that can be, yet again, extended and generalized to different types of origami. And in consequence, if I could make my method of origami scissor-hinge geometry method worked with their origami method, it could consequently, potentially, also be extended and generalized to these other types of origami of thick panels. So pretty much like the previous example, the geometry method is first to establish the geometry of the segments of the origami, its creases, its faces, and its inherent geometry, and then to apply the method, the form generation method of relative ratios, to the thick origami. So this is the beginning, which is, as you can see, just a square. And you take midpoints, and you build in an inner square. And then we end up with these 2 triangles. There's the bigger triangle, 6, 7, 8, and the smaller triangle, 6, 2, 7. And they have here equal thicknesses. So this is 1 thickness, and here there's 1 thickness as well. But in half of this triangle that is determined by this intersection, there are 2 added thicknesses, and they are all equal and proportional. So this is the water bomb pattern. So I'm using at the moment 6 faces, and this is one with more faces. So I'm taking literally just this square. So this is the deployment sequence, the folding sequence of the water bomb pattern. And I take this triangle, and again, I divide it into other set of segments and subsegments just to give it some reinforcement, because otherwise it may be a bit frail, the prototype. And the same for the other triangle. And what I do, I divide it by midpoints and diagonals, and again by triangulation. That works very well. And in reality, out of all of these, in fact, I only have, out of all of these, I only have 2 different types of segments that I can calculate, and then I can actually duplicate and transfer this everywhere else. So for instance, I have this segment as 1, but this one is equal to this one, to this one, to this one, to this one. Basically, all of the verticals and all of the horizontals are the same as this one, and the same for the other one. And here, all of the diagonals are equal to this one, and 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 the other ones. So in fact, I only have to calculate 2 segments, S1 and S1 and S2. And I tried actually different options, but I chose to apply 3 equal ratios to the first segment, and in the second segment, I divided into this smaller 2 other ratios. So the whole structure is done with originally 3 different types of scissor units, but later on, again, they will be put, and the layers will be joined in order to make a trellis and to make it more structurally efficient. Therefore, there will be other type of sizes, just simply because I've unified these different type of sizes of scissor units. So here we can see this triangle, the origami triangle, is this one now made with scissors and all the reinforcement. And these are the creases, which are fixed segments. And now instead of fixed segments, I've got points along a virtual line. And the same with the other one. So here I've got 1, 2, and 3 thicknesses, and therefore I have 3 layers of scissor units. So this is a three-dimensional view of what the theoretical model would be like. So this is the origami of thick panels by Chempen and Yu, and this is the origami scissor hinge pattern that I have developed. So here we've got the crease, which now, instead of being a fixed segment, is now points along a virtual line in space and can therefore expand and contract. So here is the folding and unfolding process of the origami scissor hinge pattern. And here is the expansion and contraction of the water bomb origami of thick panels. And this expansion and contraction could happen at different stages. So basically, origami scissor hinged deployable structures is a new technology that didn't exist before, and is the first expandable origami. And also, it's a new hybrid type of deployable structure, and it has unified two different types of deployable structures that throughout history have been separate. And there has always been, in this field, there has always been research done on the theory side of things and on the practice side of things. So sometimes advancements are done through practice, and then sometimes new ideas are developed, and then an application is looked for them. And this new technology, origami scissor hinged deployable structures, has new kinetic properties that didn't exist before. It has, we could say, two deployments. It has 2 degrees of freedom. So it can fold and unfold as an origami, but it can also expand and contract. And these are 2 kinematically separate, so they could work independently or simultaneously, and that's why we say that they have 2 degrees of freedom. And also, this is not one single structure. This is a method that can be extended and generalized. So you could potentially make more origami scissor hinge patterns. Now, a critical condition to apply this method is that the thick origami has to be made of equal or proportional thicknesses. Therefore, this technology allows a maximum expansion and contraction with a minimum energy input, and it has a high ratio of deployed versus stowed configuration, and therefore it could be useful for aerospace applications or transportable or just simply transformable components in permanent architecture. And all of these qualities, that it can be rapidly built, that it's light, that it's adaptable, that it can make efficient use of space, it means that this technology embraces the concept of sustainability. And we live in an age where life is actually an ongoing experiment. We live in a society that is constantly changing, and our buildings have to readapt and change with many different programmatic possibilities as society evolves or changes. So therefore, this technology offers new possibilities for architecture. But not only architecture, also aerospace or robotics, or potentially just kinetic art as well. And finally, I wanted to show one of my drawings. This is the original drawing is just pencil on paper, and this is a space elevator. As you can see, this is the Earth. I actually drew it the way around, but when I finished drawing it, I turned it around, and I prefer it that way. So this is a space elevator coming from Mallorca. That's where I am from. And I did this drawing because I was inspired, and I read about the deployable structures and space architecture. And this was really the beginning of an interesting journey. I have also brought here some books. This is a book I published in 2015, and it gives a broad overview of different types of deployable structures. If you are interested, please let me know. Also, these are all the recent publications about the work I have just shown you. So a new hybrid type of deployable structure has just been published in the Journal of the International Association for Spatial and Shell Structures, and it has also been published in the Origami 7 books, which is the book proceedings of the 7th International Conference in Origami, Science, Education and Art, because all of this work is at the very intersection of science and art. And the last one is the publication of my method for scissor units, And if you would like to download any of these publications, they're all in my website. You can go to my website and look for them and download it and find pictures and find more information if you are interested. And thank you very much.